All right, so to start off with, let's look at what's called resonance, okay? We were looking at the structure for O3, okay? And if we drew the Lewis structure for O3, what we got, or we ended up with, was a Lewis structure that looks something like this, okay? Where we had electrons arranged in this fashion here, okay? If you don't remember this, go back and watch this video, but you should all be able to get this Lewis structure at this point. Again, make sure your dots look really nice, everything looks nice and neat. Make sure these dots aren't all stuck together. There's a nice separation between these two, and these two. Anyway, the point here is that what we're looking at, in order for, here's the problem with this, by the way. Here's the issue. If we look at this structure, okay, what this is telling us is that there's a single bond here and that there's a double bond here. Now, single bonds by themselves are longer than double bonds, and they have less energy than a double bond. So if we're looking at this Lewis structure, we should see a distance between these two. If I call that distance 1, and this one I call distance 2, well, I should see a difference in those distances. When we look at the data for ozone, distance 1 equals distance 2. Okay, that's a problem, because that's not what our Lewis structure is showing us. The other problem is that the bond energies for both of these are about the same, but our Lewis structure is not indicating that. So there's a limitation to Lewis's simple model, because Lewis didn't realize, because his model came before quantum mechanics, that electrons aren't localized. This is called the localized model. What that means is that electrons are in between these two nuclei of the oxygen atom, and these 4 electrons are between these. But remember, Heisenberg's uncertainty principle says we don't really know where the electrons are. We know that they're most likely in this atom and most likely in that region called the internuclear axis between the two nuclei, but we can't say for sure where they are. So there's a problem. The electrons are zipping around throughout this whole thing, that these electrons are not just here, but they're also over here at the same time. Yeah, I know, it's kind of crazy. So we need to draw a Lewis structure that is going to show that. Okay, so what we have to do is we have to draw the same Lewis structure that we have here. Okay, draw it again, and what we're going to do is we're going to replicate the bonds on both sides. So I'm going to have that single bond here. I'm going to draw this, and this is what's called resonance. Now, I'll talk about how you know resonance is going to happen in just a second, but to fix this model, what I do is I draw brackets around this, and I draw a double arrow pointing in both directions, draw another bracket, and I just duplicate the same structure, but I change the bonding. Oops, I probably should change the bonding, right? So I'm going to change the electrons on both sides. So now I'm going to have a double bond over here and a single bond on this side. Now, I'm not flipping the molecule over. Don't misinterpret this. I did not take this molecule and just flip it over and get it over on this side. I kept the oxygens in the same spot as they were, so they didn't move. What I moved were the electrons. It's the electronic arrangement that is changing. The electrons on either side are different, and they're going to be replicated on both sides. That is what's different, okay? Okay, so there is your correct structure for ozone. So ozone would have to be represented like this as a resonance structure. So how do you recognize when something has resonance? Well, what you're looking for is a central atom that has atoms on either side of it or all around it that are the same. Now, it doesn't have to be the same as the center atom. It's just that they have to be the same atoms on the outside, meaning 2 oxygens on the outside. Okay, and therefore the bonding also has to be different, and that's the second criteria. So let's take a look at another example. If I take a look at CO3 minus, okay? If I look at the carbonate ion and I draw the Lewis structure for the carbonate ion, I'm going to end up, and I'm not going to go through the rules and the steps on the Lewis structures, I'm just going to draw them out here because I know what they look like. So I'm going to draw 1, 2, 3 for the oxygen. I know this is what it's going to come out to when I follow my rules for Lewis structures. Okay? So what I'm looking for is that I have an atom that has a central atom surrounded by elements that are the same. So 3 oxygens surrounding that central atom. And the bonding is different. So really what you're looking for first is whether you have all the same bonding or if you have differences in the bondings. Well, in this case, since I have differences in the bondings and the atoms are the same, now I'm going to have resonance. Now let's say, for instance, that this were hydrogen here. If this were a hydrogen, there wouldn't be any resonance in here. It's only between the 2 oxygens. So the resonance only occurs between the elements that are the same with different bonds. All right, so charge of -2, by the way, not -1. Okay, so charge of -2. Now, one other thing that I have to do is if I'm doing ions, I need to put that -2 out here. So if I have an ion, no matter whether it's resonant or not, I still put brackets and I put a -2. Okay, so the brackets have dual use. Now, for this one here, I'm going to have to draw 3 of these structures. I have to draw 3 of them. I'm going to put the double bond here. And again, take your time. I know that you can kind of get sloppy with these. So make sure that you go back and fix any dots that look like lines or you're unsure. I'm telling you, you don't want to lose points on a simple Lewis structure because you were sloppy with the dots. And I see that quite a bit. Brackets around this, brackets here. Do the same thing for the third one. 2 minus, 2 minus. Okay? And there is your resonance structures for carbonate. Okay? O3.